The continuous time Fourier series can be given in two different forms. The first one is a trigonometric Fourier series. Let's assume that you have a periodic signal x of t with fundamental frequency omega 0. Then the trigonometric Fourier series allows us to express x of t as a constant and an infinite sum for n equals 1 to infinity of cosine and sine terms, where the frequency of the cosine and sine terms are multiples of the fundamental frequency omega 0. And the cosine terms are weighted with factors an, and the sine terms are weighted with factors bn. So we see here that the frequency omega 0 reappears again as multiples here in the frequencies of the cosine and sine terms. So this is a given as soon as we know x of t. When we calculate the trigonometric Fourier series, what we actually calculate is the offset a0, the coefficients an, and the coefficients bn. a0 is given by 1 over t0 over the integral over the length of t0 of x of t dt. t0 is the fundamental period of the signal x of t, and it's related to the fundamental frequency by the formula t0 is equal to 2 pi over omega 0. This notation here implies that we have to take the integral of x of t over one full period t0. So we could take the integral of x of t from 0 to t0 or from minus t0 to 0 or any other integral as long as its length is t0 long. The cosine coefficients an are given by the formula 2 divided by t0 times the integral again over one full length of the period t0 cosine of n omega 0 t x of t dt. And the coefficients for the sine terms, bn's, are given by the formula 2 over t0 times the integral again over one full length of the period t0 sine of n omega 0 t x of t dt. When the signal x of t satisfies some special properties, the calculations of a0, an, and bn can be simplified significantly. For example, a0 is equal to 0 if x of t has 0 mean. When you look at the expression of the trigonometric Fourier series, you see that the cosine and the sine terms all have 0 mean. So the part of x of t which describes the offset if x of t has not 0 mean is a0. So if x of t has 0 mean, it can be described just with the cosine and sine terms, and it does not need to have this factor a0. So a0 must be equal to 0. Also, the coefficients a0 are equal to 0 if x of t is an odd function. This even includes a0. And this is true for all n. Since cosines are even functions, they can't contribute to a signal x of t which is purely odd, so a of n has to be 0 for all n's, and the signal is only described by sine terms, so that we only have coefficients bn. And the coefficients b of n are equal to 0 if x of t is an even function. And this is true for all n again. This again follows from the fact that if x of t is a purely even function, it can't be described by any odd sine terms. Instead, it's only described by an infinite sum of odd cosine functions, so that the coefficients bn must be 0 for all n. And the last property is that all coefficients a0, an, bn for all n are real valued if x of t is a real function.